Good morning, everyone. So it's time to start our eighth recitation of CS2100. So thank you for joining. Today, after a couple of announcements, we'll do two simple problems related to sets because that's going to be in quiz 3. And then we'll do a couple of problems on relations and properties of relations, which is what was covered in the last two lectures. And our TA Mark joined, and so he will be keeping an eye on chat and raised hands and so on to make sure that if you guys have any questions, he will ping me. One more thing I want to say is that, we are not having large crowds anymore. Initially, there was like 50, 60 people joining. Now we are usually at around 30. So you're more than welcome to just, when you have a question, you can unmute yourself and just speak up. I don't think that's going to cause a lot of kind of confusion and so on. So please feel free to do that. Another thing I want to just briefly talk about, maybe some of you already noticed this. We have 4 recitations, 4 discussions. They are not identical copies of each other. So sometimes I have a little bit more time. I do one more problem or something like that. I think Professor Phillips tends to be a little bit faster than me. At least that's what I gathered based on talking to her. And so she might solve a few more problems, but she also might go through them faster. So you can kind of pick and choose which recitation suits you the best. And also they're all recorded. So you're more than welcome to quickly kind of go through them after they're done and see if there are things in other recitations that you maybe missed. But we do cover everything that is needed for the quiz. Okay, so let's get it started. So a little bit about quiz 2. I'm sure we all seen grades are out. So this is the grade distribution for quiz 2. And note that, sorry about this. It's a little bit worse than quiz 1. Quiz 2 is typically, let's say, the hardest quiz, I would say, in this class. But this is not bad. If you look at this, almost 20%, almost 1/5 of the class scored above 95, for example. More than half of the class scored above 80. So these are good scores for quiz 2. And don't forget that we do drop the lowest quiz grade. So if you didn't do well on quiz 2, but you do well on other quizzes, you can still get a really good grade. Okay, so a couple of announcements. So quiz 3 is going to be next week on Tuesday, as usual. You have a 1-hour window between 7:30 a.m. and 4 p.m. Hopefully you already know the drill, know the routine. After this 1 hour, you have half an hour to submit your quiz. Use that half an hour carefully and smartly, so make sure that you submit it. We won't be accepting quizzes submitted outside of grade scope anymore. So quiz 3 will be on sets and Boolean algebra. So that's only chapter 3 in your textbook, or lectures 8, 9, and 10. Of course, in these lectures and in the last recitation, we did some proofs about sets. And these proofs build on some of the techniques we learned in chapter 2. So you can definitely expect that there will be questions on proofs about sets. The form. If this is the definition of one set and this definition of the other set, prove that the first one is a subset of the second one and things like that. So element-wise proofs. We also released homework 4. And due to quite a few requests that we release solutions for quizzes, we won't quite do that. But going forward, we will be solving quiz problems during discussions after the quiz. And we will also be posting some of them on Piazza. So keep an eye on those and show up for these discussions. For example, this Thursday, TA's already prepared the discussion session slides, and they'll be solving during discussions a couple of, I would say, more challenging problems from quiz 2. So if you struggled with quiz 2, or you're just curious what the solutions are, come to discussion sessions. It's kind of important also to learn this if you didn't do well in quiz 2, because we do also have the final exam, and the final exam includes all the material. So for example, it is a pretty high probability that there will be, one proof by induction in the final exam. So it's good to learn this, how to solve these problems. Okay, so these are the announcements that I have. Any questions so far? Okay, so let's do a bunch of practice problems. So the first two are on sets. They're rather simple, I would say. So they're related to your quiz 3. So why don't you try to do this one on your own first? I'm not going to do breakout rooms now. I'm going to do it later. This one is kind of too simple for breakout rooms, I would say. So you have two sets, A and B. They're a little bit weird because some of their elements are sets themselves, but that's totally fine. We already learned that. And you have to write out the result of the following set operation, A times B. So I'll give you a minute to write this down, and then I'll solve it for you. Okay. So this operation is also called Cartesian product. And it generates a set of pairs of all possible pairs between sets A and B. And so it's going to be a set. And the first pair is going to be, the order doesn't matter. So A, comma 1. And then we have A, comma set 2, 3. And I messed up this one. This should be parentheses. Then we have this element set B, comma 1. And we have B, comma, 2, 3. So that's the solution. One thing to keep in mind here is that the order matters. So A Cartesian product with B is not equal to B Cartesian product with A. So B Cartesian product with A would be the same as this, but all the pairs would be flipped. So it will be 1 comma A, 2 comma 3 comma A, 1 comma B, 2 comma 3 comma B. Okay, so this is hopefully a simple one. Any questions about this one? Okay. So let's do one simple proof. We want to prove that any set A is a subset of itself, and we can do this using a direct proof. It's a very simple proof. So what is the definition of a subset? If we have that for all x, x x element of S implies x element of T, then S is a subset of T. So that is the definition of a subset. So all elements sorry, I apologize. I kind of smell smoke in my office, which is a little bit disconcerting. But some kind of construction is happening on the building, so I hope everything is fine. Wow, this is weird. Okay, so this is the definition of a subset, and it is clear that it is true for all x. If x is an element of A, that implies that x is an element of A. And because of that, A is a subset of itself. So this actually finishes the proof. And it's so simple that maybe it even doesn't look like a proof, but that actually does it. Any questions about this one? Okay. Make sure to practice element-wise proofs for quiz 3. Make sure also to practice to learn properties about sets. You remember that true-false kind of question and so on. Those are the kind of things that would likely appear on the quiz. Okay. Okay. Switching to relations, which is what we covered in the last two lectures. This is just a reminder about all the possible relation properties that we covered. So if R is a binary relation on A, then R is reflexive if and only if A comma A is element of R for all A in A. So if you remember the way Bay kind of explained this, all elements, when you draw a diagram, should have a loop around it. It's irreflexive if that's not true. It's symmetric if the fact that AB is in R implies that BA is in R. So it's symmetric if you have these sorts of situations. So it's antisymmetric if that's not the case. And it's transitive if you have AB and BC in R, then you have AC as well. So the way you would kind of sketch this out, if this is A, this is B, this is C. If you have an arrow from A to B, and from B to C, then there is an arrow from A to C. So this is just a reminder that we already covered this in the lectures. But we'll use these properties. We'll have to do proofs of these properties and so on. Then also recall, we then defined a couple of different types of orders. So R is a partial order if it's reflexive, antisymmetric, and transitive. The way to remember this is RAT. Of course, for the quiz, you can have one index card or cheat sheet, right? So, write down these properties there so you don't forget them. So apart from partial order, there are other types of orders. There is a strict partial order, which is when a relation is antisymmetric, transitive, and reflexive. There is a total order, which is partial order plus this additional property that every pair of distinct elements are comparable. And then you have strict total order, so the same as total order, except it's irreflexive instead of reflexive. So those are different types of orders. And so another thing that we introduced is an equivalence relation. So that's a relation that's reflexive, symmetric, and transitive. Again, that's just a refresher from the lectures. Okay. And so once we introduced the equivalence relation, we also showed how it relates to a set partition. So if you remember, a set partition is a set consisting of sets such that each element of the set partition is a subset of the original set. Their intersections have to be empty sets, and their union has to be the original set. So those are the properties of set partition. And so now we have this simple problem. So we have a set A, which consists of 0, 1, 2, 3, 4, 5, 6. We have this relation R on set A, and xy belong to R if x minus y is divisible by 3. And now the question is, what is the partition of A induced by this equivalence relation R? So the partition is always a set, and it's a set of sets. So you will have a bunch of sets here. And this equivalence relation induces a partition. And so all elements of each element of this partition, all these pairs have to belong to R. So that's how you generate the partition using this equivalence relation. So, so this is a rather simple question. I'll give you maybe a minute to try to do it on your own, and then I'll solve it for you guys. Okay, so let me do that. By the way, I also apologize if there is noise in the background. I have a pretty good microphone, but they're drilling somewhere above me, so you might hear a little bit of this noise. You sometimes I would stay at home, but we are redoing our roof, and so so our house is currently way noisier than even this. There is nowhere to go. Okay, so 0 would go with 3 and 6. So all pairs from this set belong to this relation R. And then what else? 1 would go with 4. And 2 would go with 5. So that's the solution to this problem. Any questions? No. So the order doesn't matter. So there's a question if the order matters. So note that these are all sets, and so the order of the elements within the set doesn't matter. Pairs are different, right? If you have a pair, the order matters. In sets, it doesn't matter. So so the order doesn't matter. Any other questions? Okay. So these were kind of the warm-up problems. So let's get to something more extensive. Okay, let's do. I have 2 proofs about relations. I'll do the first one, and then we'll do the second one together using breakout rooms. So we have this relation R on z times z. So z are integers, and it's defined with a minus b is even. And want to prove that it's reflexive, transitive, but not a partial order. And now I need my reminder of all the definitions. Okay, where's my pen? So let's do reflexives first. So remember the structure of these proofs. They're always direct proofs. So you start with, looking at the property. You start with the left-hand side with your assumptions, and then you want to derive the right-hand side. So to prove reflexive, we have some A element of the domain. And from there, we want to derive that A comma A is an element of R. So that's the skeleton of the proof. And we have to fill in the middle, right? So A is an element of Z. And then we plug it into this expression, A minus B is even, or A minus B. And we want to show this even, right? So we have A minus A. And that is equal to 0. And 0 is equal to 2 times 0. So it means it's even. And from there, it follows that A comma N is element of R. So that finishes the proof that it's reflexive. So reflexive is usually the easiest proof. Usually it's really straightforward. Okay. The second one we want to show is that it's transitive. Let me prove that here. Okay. In this case, we have let A be element of R and BC element of R. And we want to show, derive from this, that AC is element of R. And again, we have to fill in the middle, right? So if A comma B is an element of R, then we know that A minus B is equal to 2 times K, because it's even, where K is an element of Z. And we also know that B minus C is equal to 2 times some L, where L is an element of Z. And I'll need a little bit more space, so let me just clean this up a little bit. Okay. We can add this up now. And B cancel. And so we get A minus C is equal to 2 times K plus 2 times L. And that is equal to 2 times K plus L. And that is equal to, due to closure of plus, is equal to 2 times M, where M is an element of Z. So we just showed that A minus C is even, and hence A comma C is an element of R. So we show that it's transitive. So we show that from the assumption that AB is an element of R and BC is an element of R, we can derive that AC is an element of R. So that's show that it's transitive. And now we want to show that it's not partial ordering. So how do we do this? We want to show that it's not antisymmetric. So we can show this by finding a counterexample. And there are many counterexamples that you can find. A simple one that I found was pairs 4, 2 and 2, 4. So both of these belong to R. However, 4 is not equal to 2. And hence it is not antisymmetric.
We have a question.
Yes.
We can't show that this is symmetric, right? Because some relations can be both symmetric and antisymmetric.
They can be neither. Is that the question?
I think so.
Let me think a little bit about this. I have to remember the properties always. Yeah, they can be neither symmetric nor antisymmetric. So the fact that we show that it's not antisymmetric does not necessarily mean that it's symmetric. But it might be. I mean, we can try to prove it. So let's see. Symmetric. If AB is an element of R, then BA is always an element of R. So we can try to prove that it's symmetric. Let me do, actually, are there any other questions while I work on this?
I think we have a question. It says, if a relation is only arrows to elements themselves, then isn't it both?
If it's only arrows to themselves. I mean, you can have a mix of, you can have some pairs that are symmetric and some that are not, right? So that will create then a relation that is neither completely symmetric nor completely antisymmetric. Okay, so symmetric. So we have let AB in R, and we have to show that BA is also in R. So if AB is in R, we know that A minus B is equal to 2 times K, where K is an element of Z. And so if we multiply this by -1, we get that B minus A, so times -1 is equal to 2 times -1 times K, which is equal to 2 times some L. So it's, and from this, it follows that B minus A is even, and therefore B comma A is element of R, and therefore it's symmetric. So this proves that it's symmetric. Okay. So it's not antisymmetric, and in this case, it is symmetric. Any other questions?
Is it possible for a relation to be neither reflexive nor irreflexive?
Okay, I have to think about this myself. Reflexive, neither reflexive nor irreflexive. Yeah, so it will be a relation that looks like this. So maybe something like this. So one of the elements has this little loop. So this guy is, let's say, reflexive. But this other one does not have a loop. So it's not reflexive. And when you look at the irreflexive, it's the other way around. You know, they all have to have that property. And in this case, they don't. So this is an example of, small example of a relation that is neither reflexive nor irreflexive. Any other questions?
Yeah, I'll just voice this one. So does this mean that a set can't be called reflexive, symmetric, or transitive unless the entire set is transitive, reflexive, or transitive?
So these are properties of a relation. So that's the first thing, not of sets. And I didn't quite understand the question. So a relation can be, for example, reflexive, transitive, and antisymmetric. So but whenever whenever you have a relation, actually I have questions like that as well. Whenever you have a relation and you have to establish these properties, you have to look at each one of them in order. If you determine it's not reflexive, you cannot automatically say, oh, then it must be irreflexive. No, you have to check reflexive, irreflexive, symmetric, antisymmetric, transitive, kind of one by one, all of them, if that makes sense. Any other questions? Okay. We can go into more details on this, but I do want that we do one more proof. And I'll give you maybe 7-8 minutes to try to prove this on your own. I'll do breakout rooms. So you have another simple relation. It's a little bit more complicated than the previous one, but not too bad. And you want to prove that it's an equivalence relation. And so you want to prove RST. You want to prove that it's reflexive, symmetric, and transitive. So we've done reflexive already, and we've done transitive. Symmetric is not too hard. It's easy to do. So why don't you try to do this? And then we'll meet again. And I'll solve it with you. Okay, breakout rooms. Mark, I will move you to room 1. Somebody's there all alone. So maybe just join room 1 and help out that person. Thank you. Okay, welcome back, everyone. I hope that wasn't too hard. So let me quickly do this. So it's very similar to the previous problem. So reflexive, we have we have some A element of Z. I'll go quicker to this now. So then if we plug it in, we have A squared minus A squared, which is equal to 0, which is equal to 3 times 0. And because of that, A comma A is an element of R. So that finishes the reflexive proof. Then symmetric. So we just did it for the last one. So we have let A be element of R. So then A squared minus B squared is equal to 3 times M. Multiply both sides by -1. So we get B squared minus A squared is equal to 3 times -1 times M. And now that is equal to, we have closure multiplication. That is equal to 3 times some n, where n is element of Z. And therefore, B comma A is an element of R. So that finishes the symmetric. And the last one we need is transitive. So we have let A comma B element of R and B comma C element of R. So if AB is in R, then A squared minus B squared is equal to 3M. And if BC is in R, then B squared minus C squared is equal to 3N. If we add this up, B's cancel, and we get A squared minus C squared is equal to 3M plus 3N, which is equal to 3 times M plus N, and that is equal to closure of plus, that is equal to 3 times K, where K is an element of Z. And therefore, A comma C is an element of R. So that finishes the transitive proof. And so we proved that it's transitive, reflexive, and symmetric, and that means that it's equivalent relation. Any questions about these proofs? Okay, we have 3 minutes left. Let's do a quick one. So we want to identify for these relations what type of ordering there are. And let's pick one. Let's do R2. So R2, we have this set A of numbers, and R2 is a relation over this set, such that the size ST is an element of the relation if the number of elements in S is less than the number of elements in T. And now we want to see, is this relation reflexive, irreflexive? What else do we have? Symmetric, anti-symmetric, and transitive. So is it reflexive? So that means if you plug in, the same set, does it belong to the relation? So the answer is no, because we are going to get, if the size of the set is 2, we are going to get 2 less than 2, right? That's false. So it's not reflexive. An example would be, right, the set that contains, sorry, set is covered for me here, so I want to find it here. So example would be, does this belong to R? It doesn't, because the size of this is 1, the size of this is 1, and they're not less than. Okay, is it irreflexive? Right, so it's irreflexive. So you will never have a loop around yourself. Then is it symmetric? So if B is in R, is it true that BA is also in R? So that's not the case, because if left set is less than the right set, if you flip them, then this is not going to hold. So is it antisymmetric? So if AB and BA are both in R, that's only if they're not the same. If AB and BA is in R, that's only if they're not the same. So it's antisymmetric, so that's true. And is it transitive? So it is transitive. Okay. So it's a strict partial ordering, because it's antisymmetric, transitive, and irreflexive. And is it the total order? So are all elements comparable? Let's say comp. So every parallel element, either AB is in R or BA is in R. So that is not true, because if their sizes are the same, then neither AB nor BA belongs to. Oh no, they have to be distinct. Yeah. Okay. So it is comparable. So it's strict total order. Okay, so I think I did this pretty poorly, but the way to, because I was running out of time and some kind of rushing, the way to do this, we are not looking for a proof here. So you either have to find a counterexample, or you kind of have to convince yourself, no, it holds, by just drawing examples from this relation. And then you have to see all the properties that hold, and based on that, you can find out which order it is. And we already talked about this, right? If you determine that it's not reflexive, that doesn't not automatically mean that it's irreflexive. So you have to check all of these individually in sequence to be able to determine this. Okay, I have any quick final questions? We have to wrap up here. I'll post the notes online as usual.
How would this problem change if there was duplicates in the set A?
Good question. It wouldn't change at all because a set cannot have duplicates. So that's something that people often stumble on. So this set is the same as this set. And it's the same as so this is just, all these three are just a different notation for this set. So the way we define sets, if you write something like this, that does not mean that there are two twos in this set. There are no duplicates in set. So there's still just one two. And so that's why we write it kind of in the shortest possible notation using this, but they're equivalent. Any other final questions?
You know, you used the closure of addition a couple times in the
Yes.
solutions. Could you walk me through what that means exactly some more?
Okay, good question. Yeah, we did that a lot in when we were doing proofs, right? You know, the material that goes into quiz 2. So basically, I had something like, you know, K plus L, where K and L are integers. And I want to do a substitution here. I want to introduce, you know, a replacement for this K plus L so that I get into appropriate form, right? Maybe I have something like this. And I want to get to 2 times M. So I can replace K plus L with M only if the addition of 2 integers is also an integer. And we know from we know that integers are closed under addition, subtraction, multiplication. That's a theorem. You know, it's in the books. We're not going to prove it. You don't have to prove it. You can just use it. So because integers are closed under addition and K and L are integers, then we know that K plus L is an integer as well. And so we can introduce this fresh variable M that stands for K plus L, where M is also an integer. If I had 2 times K divided by the L, then I would not be able to replace this with 2 times M, because integers are not closed under division. So making this step does not work. Does not work. So that's where this closure comes into play. So you can do this substitution only if the result of your expression is also an integer.
Okay, so it only works with addition and multiplication?
And subtraction.
Okay.
But not division. Good question. Any other questions? Okay. Okay, thank you, everyone. Good luck with the quiz next week. Come to office hours if you have any questions.